Welcome to this session on file handling and templates. Today we will move into another essential area of C++, that is code reusability and data persistence. So our topic is file handling and templates. File handling allows us to store and retrieve data permanently even after the program stops running. And templates, on the other hand, helps us write type independent and flexible code that can work with any data type. So together with these two concepts, we can build an efficient and reusable software systems. So here's what we will be covering in this lecture. First, we will explore text and binary file handling. We will learn how to read and write objects, and then we will shift our focus to templates. That is one of the most powerful features of C++. We will discuss both the function templates and class templates, and finally we will have a quick overview of standard template library. So by the end of the session, you will have a clear understanding of how C++ handles data storage and generic programming. Before diving deeper into file handling concepts, let's quickly revise the essential operations that we can perform on files in C++. So we will go step by step through examples that show how to check if a file exists before reading, detect the end of the file while reading, read and write data to file, work with file modes and simple word counting. So these examples will help you build a strong foundation for handling both the text and binary file. Let's start by checking whether a file exists before trying to read from it. So in this program, we create an input file stream using ifstream class and attempt to open a file named aa.txt. So the key function here is failed. It returns true if the file could not be opened, and usually because it doesn't exist, or maybe there was a permission issue. So inside the if block, we can display a message or handle the error gracefully. Otherwise, if the file opens successfully, we proceed with our reading operations. So always remember to close the file after use with the close function to release the system resources. Next, let's see how to check whether we have reached the end of a file. So EOF, end of file function, in the file stream helps detect when no more data can be read. So in our example, we use a loop, while loop. So this means while not at the end of file, keep reading. Inside the loop, we read the numbers from the file using that angle bracket and notation like we usually do with scene and scene operations. So in this we are dealing with files, so we write file object name fin, and we try to read the file data into data variable, and then print each value to the screen. So each iteration continues until the end of the file is reached. So this pattern is very common when reading line based data from files. Now let's focus on a cleaner pattern for reading data from a file. We again open a file using ifstream fin object, and we use a loop to extract integers until the end of the file. Notice how we first read a value before entering the loop, and then keep reading new values at the end of each iteration. So this avoids reading invalid and duplicate data after the end of file. So the program prints each number to the screen, one per line, showing exactly what is stored inside the file. As always, the stream is closed with fin.close when we are done. Then writing to a file is just as simple. We use a fstream class and open the file in the output mode using that scope resolution operator and iOS. So here we write integer values to the file called file.txt using the insertion operator, that sign that or brackets that we usually use with cout operators. The loop continues while the data is not equal to 16. So writing each value followed by a new line. So this will create a file that contains numbers from 10 to 15. When finished, we always call close function to save and release the file properly. So this process is called serialization of simple data. So we are writing program data into a persistent form. Now when working with files, we use open modes to specify how the file should be used. The syntax is myfile.open then as a first argument is the file name, and in the second argument we try to write a mode. So in is for reading input from the file, out means for writing output to a file, APP is for appending data to an existing file, binary is used for working with binary files. So these modes can be combined using OR operator, like the last one example we have written out and append, and we have combined them with OR operator, meaning the file will be opened for writing and appending, for both writing and appending. Now let's look at a slightly more interesting example of counting the number of words in the text file. So the idea here is simple. We will read the file content line by line, then check each character in that line. Every time when you encounter a space or a tab or a new line, we will assume we have reached the end of the word, and then we will increment our word counter accordingly. So let's see how it is done in code. We start with including the required headers, IO stream for console input and output, F stream for file handling, and string, that because we will be reading entire lines as strings. Then we create a input file stream, my file, and open file.txt in input mode using that scope resolution operator and in. The first check we perform is important. We test whether the file exists by calling the fail function. If it returns true, we print a message saying that file doesn't exist and skip the rest of the code. So this prevents runtime errors when we try to read maybe a non-existent file. So if the file is successfully opened, we initialize two variables, I and WRD, that is for word. So I is used to iterate through the characters of the string, and word basically will store our word count. Then we enter a while loop, meaning keep reading until the end of the file. So inside the loop we use getLine function. So getLine function has three arguments. First one is again your file stream object, second one is the string, and third parameter is an optional delimiter. It tells the programmer or a program to read the file until it encounters an static, for example. So normally we could just write getLine myfile, str, that's it, to read each line. But third argument is also can also be inserted, but this is an optional delimiter. Once a line is read into a string variable str, we go through each character using another while loop. So inside the loop we check if the current character is a space or a new line character or a tab. So each of these characters signals a word boundary. So we increase the word counter whenever we find one. After finishing all the lines, we simply display the total count on the screen using cout word. Up till now we have been working primarily with text files that contains human readable data. For example, when we save a list of numbers or words in a .txt file, we can easily open it in a text editor and see what is inside it. But in many applications, especially those that deal with large amount of numerical data, images, audio or video maybe, that is storing data in text format becomes inefficient. So this brings us to a more powerful form of file handling, that is binary files. So the main reason for using binary files is speed. When we store or read data as text, every number must first be converted to characters, and when we read it back, it has to be converted back into numbers. Imagine a 32-bit integer, so converting it into characters and then parsing it back each time introduces processing overhead. So if a program, say a video game, has to deal with millions of such numbers, these conversions add up, and that eventually leads to slowing the entire program dramatically. So binary files skip this step and they store the raw binary data, the actual 0 and 1s, directly in the file, exactly as they exist in the memory. In addition to speed, binary files are much smaller. So text files can take more space because every number or character is represented by several bytes of textual data. But in binary format, we only store the exact byte representation of the data. So the size difference matters. Small files are faster to store, transfer, or process, which is crucial in performance sensitive applications like image processing, audio playback, maybe computer games, data compression programs. So let's take a simple example, that is an executable file like a .exe file in Windows. Inside you will find values which represent machine instructions that only your processor understands. For example, an add operation and relevant instruction related to that. So these bytes are pure binary data, not textual in nature. So if you try to open an exe file in text editor, you will just see strange or unreadable symbols and characters. That is because these files are not meant to be interpreted as text. They are meant to be interpreted directly by the hardware or the software that understands the binary format. So in short, all files are binary at hardware level. They are just sequence of bits stored on the disk. The difference is in how we interpret those bits. In a text file, we interpret the bits as a human readable characters, and in binary file we interpret them as a raw data such as numbers, images, compiled instructions, sound samples. C++ allows us to handle both with ease using the same file stream classes, but with a small change in how we open and process the file. So in the next section we will see how to read and write binary files in C++ using that binary mode. So far we have seen how data is stored and managed through files, but even before data reaches the file, it occupies a memory inside our program. So a natural question arises, that is, how much memory does an object occupy? So in C++, the size of a class or an object depends on its data members, its base classes, and sometimes the presence of virtual functions and virtual inheritance. Now let's explore this step by step. So the first rule is only non-static data members are counted when calculating the size of a class or an object. So let's look at this example. We have a class A with one float data member that is of 4 bytes, one constant integer, again 4 bytes, one static integer. So this is not counted since it belongs to the class, not to individual objects. And then one character that consumes 1 byte of memory. So the total size is not exactly 9 bytes because of something like maybe structure padding. The compiler aligns the data for efficiency. So the final size of the class might be 12 bytes depending on the compiler and architecture. But the key takeaway is that static members are not included in the object size calculation. Second rule is the size of a class includes the size of its immediate base class. Here the base class B has 2 integers, 8 bytes in total. The drive class D adds 1 more integer, another 4 bytes. So the total size of D becomes 12 bytes. So this demonstrates that every drive class object contains a copy of all the base class members. Third rule involves virtual functions. Whenever a class contains at least one virtual function, the compiler automatically adds a hidden pointer, that is vptr, or a virtual table pointer. So this pointer helps the dynamic polymorphism that we have covered in the last session, connecting each object to its corresponding vtable. So each vptr usually occupies 4 bytes on a 32-bit system and 8 bytes on a 64-bit system. So in this case, B has one integer, that is 4 bytes, plus vptr 4 bytes, the totaling 8 bytes, considering maybe 32-bit architecture system. Drive inherits that vptr and adds one integer, so total becomes 12 bytes. Notice that adding more virtual functions doesn't increase the size, as all the virtual functions share the same single vptr. Now let's consider virtual inheritance. When a base class is inherited virtually, C++ ensures that only one shared instance of that base class exists in the entire inheritance hierarchy. Let's see an example. Without virtual inheritance, class D would have two copies of A, one from the B and another from the class C. But because we have declared A as a virtual base class, class D only contains one shared instance of A. That saves memory and ensures that changes in A are consistent through the hierarchy of classes. The compiler adds a hidden pointer in the derived classes to maintain the shared base linkage, which slightly increases the object size. Now that we understand how much memory an object occupies and what factors affects its size, such as data members, inheritance, virtual functions, we can take the next logical step, that is storing these objects permanently in file. Up till now, our programs work with objects only in memory. Once the program ends, that memory is cleared and the data disappears. But in real world applications such as maybe student record systems, banking softwares or games, we need to save and reload objects later. So this is where file handling meets object oriented programming. So in the next part we will explore how to read and write entire objects to the file, both in text form and more efficiently in binary form. So in this program we have defined a simple student class. The getData function allows the user to input details, and then we open the binary file named student.dat. Then a file for writing entire object byte by byte into the file, that is file.write. This means the file now stores the object's binary image, including all its data members exactly as they exist in the memory. Notice we have used iOS and that binary mode. This ensures that no conversion is done, unlike in text files. So when we open the file again with the .read function in the binary read mode, we can use this function to reconstruct the object. So this statement reads the same number of bytes that were written earlier, restoring the object exactly as it was before with all of its data members intact. And then call showData function to verify that the data was correctly retrieved. So this process forms the basis for object persistence, that is storing and retrieving objects data for later use. Now that we have seen how objects can be written to and read from the binary files, so write and read functions both take two arguments. The first one is to read the data, and the second one outlines the size of the object that we intend to either read or write. Let's discuss very important technical details and good practices that you must always keep in mind when working with object files in C++. First, remember that the functions read and write operate only in binary mode. That means whenever you open a file to store or retrieve an object, you must include the flag iOS binary in your open statement, because if you do not do this, the system might treat the file as a text file, and in that case certain characters like new line or end of file markers may get automatically converted, that basically corrupts your object data. So binary mode ensures that the data is written exactly as it exists in the memory, byte by byte. Secondly, always make sure you use the correct combination of open modes. When you are writing an object, use the out and binary mode, and when you are reading, use in and binary mode. If we want to append more objects to existing file, you can use app and binary mode. So these combinations clearly tell the compiler what kind of operation you intend to perform. Third, note that only the raw data members are written correctly using this method. If your class has pointers or dynamically allocated memory, then only the pointer address gets stored, not the actual data it points to. So when you later read the object back, the pointer will be meaningless. That is why for simple binary file input-output, it is best to use classes with only primitive and fixed size data members such as integer, floats or character arrays. Fourth, the size of object that you use in the write and read calls must match exactly for both operations. If you modify your class, for example, by adding or removing members, the object size changes, and reading back old data may produce incorrect results. And finally, it's always good to explicitly close your file after every operation. So calling file.close ensures that all the data in the output buffer is written to the disk, and it frees up the system resources. Now that we have learned how to write and read entire objects to and from the binary files, so this allows our program to store data permanently and retrieve it later, which is a major step towards real world data management. But so far, every time we have accessed the data from the file, we have done it in a sequential manner. That means one record after another from the beginning to the end. Imagine a file containing hundreds of students' records. If we want to update and display the detail of, for example, 80th student, do we really need to read all 79 records first? That is obviously inefficient, and that's exactly where the random access comes in. So in C++, files can be accessed not only sequentially but also directly using the file stream positioning functions such as seekg, seekp, tellg and tellp. So these functions allows us to move the file pointer to any location in the file to read, write or update data at that exact position without disturbing the rest of the file contents. So in the next part, we will explore how file streams in C++ gives us both flexibility and power in file handling, how the internal read and write pointers work, and how we use them to achieve direct access to objects data. So this understanding will prepare us for the next logical step, that is reading and writing specific objects at chosen locations rather than always working from the start of the file. So now let's move ahead to an important topic, that is file streams and random access in C++. Let's now understand one of the most important tools that make file handling random file access possible, that is seekg and seekp functions. These two functions are used to move the internal file pointers that controls where the next read or write operation will take place. So the term G in seekg function stands for get, and it is used for input streams like if stream to control where data is read from. Similarly, P in seekp function stands for put, and it is used with output streams like off stream to control where the data is written to. The first and simplest form of these functions looks like seekg, maybe long position and one argument long position, or seekp with position one argument. So this version moves the file pointer to an absolute byte position inside the file. So let's look at this example. If stream fin object, and for off stream we have created f out object. Then we have used file opening routines. When we write fin.seekg30, we are telling the program move the read pointer to the 30th byte in the file. That means the next read operation will begin from that exact byte position instead of starting from the beginning of the file. Similarly, fout.seekp30 moves the write pointer to the 30th byte. So the next write operation will start exactly there. So this technique gives us direct access to any specific location in the file without having to read all the previous data sequentially. So you can think of it like skipping directly to a chapter in a book instead of flipping through all the earlier pages. So this is extremely useful when dealing with structured data files. For example, when we store a list of fixed size records such as student objects or employee data, we can calculate the exact byte location of any record and jump right to it using seekg or seekp. So seekg moves the get pointer for reading and seekp moves the put pointer for writing. And in this first form, both functions move to absolute byte position in the file. Now let's move to the second form of these functions, one that provides much more flexibility by allowing us to move the pointer relative to a reference point, unlike absolute byte position. So this forms look like seekg with two arguments now. One is an offset and second one is an origin. Here offset tells us how many bytes to move. Origin specifies from where that movement begins. In other words, the pointer's new position is determined by taking the origin point and then adding or subtracting the offset value. So C++ defines three possible origin constants. Number one is with beg, that is the beginning of the file. Second one is cur, meaning the current position of the file pointer, and finally end for the end of the file. So let's understand it through few simple examples. For example, let's see the first one, pin.seekg with two arguments 10, and in the second argument we have supplied the first origin constant, that is the beginning one. So this means move the get pointer 10 bytes from the beginning of the file. Second one with first argument as -5 and then end marker means move 5 bytes backwards from the end of the file. And finally for the cur, that is current position of the file pointer, this means move 20 bytes forward from the current position of the get pointer. So the same logic applies to seekp versions for output streams, allowing you to position the right pointer anywhere in the file relative to the beginning, current position or end, like we have done with the seekg. So this version of seekg and seekp gives us a true random access control. We can move forward or backward through a file very easily. So this is extremely useful when we need to skip headers or metadata at the start of the file, or we want to jump to the specific record, or to go backward to reread or modify something. So together of these two forms make it possible to navigate through the file very easily. So now we have learned how to move the file pointers using seekg and seekp, let's see how we can know exactly where these pointers are at any moment. So C++ provides two very useful functions for this purpose, tellg and tellp. Just like before, G stands for get and P stands for put. Tellg tells us the current position of the get pointer in an input stream, while tellp tells us the current position of the put pointer in an output stream. When we run this code, we will see that tellg reports the exact byte position in the file each time, 0 at the beginning, 10 after moving forward by 10 bytes, and the number close to the total file size -5 after the final seek. Similarly, tellp works for the output file streams, showing where the next write operation will take place. So these two functions are extremely useful when performing random access file operations. Let's now see in action how the write pointer or the put pointer moves inside a file, and we will also observe how tellp reports its position after writing. Here is a program that writes the text BSCF19M001, that is a roll number, into the file. After writing, the put pointer is at the end, just past the last written character. Tellp reports that position, so it tells us how many bytes have been written so far. Then we write seekp function with 6 and beginning mode, and that function moves the write pointer to the 6 byte from the beginning of the file. At that point, when we write A, the character at the position 6 is overwritten by A, showing that we can directly modify any part of the file by moving the pointer first. So this is the essence of random access. Here we again open the file for output and write BSCF19M002. The tellp call gives us the current position after writing these characters, so it is right at the end of what we just wrote. Now instead of moving from the beginning, we use iOS and that current mode, which means move relative to the current position. So the first argument we have written 3, that means move the pointer 3 bytes forward from where it was, and then the program writes BSCF19A002 starting there. This way we can skip or leave gaps intentionally in file, for instance to reserve space for future updates or structured records. Finally, the third example adds a twist by using that end mode. Here the program writes BSCF19M002 and then that underscore and asterisk into the file. Now notice the line file.seekg with -1 and that ending constant. So it moves the get pointer 1 byte before the end of the file. But since we are still using the same file stream object, this effectively sets the position for writing to just before the end. Then we write fall 2019 at that location, meaning our new content overwrites the file from near the end. So this shows us how seekg and seekp can even work relative to the end of the file, showing us to append or modify the tail portion of the file very efficiently. So in summary, tellp tells us know where we are, while seekp let us go wherever we want inside the file. Now let's look at a very interesting and practical example, that is how we can directly access a particular person's record from a file without reading all records one by one. So this is possible using random access again with seekg function. So this class only has one data member age and two functions: get data to input a person's age and show data to display it. So in real world program, the class might include name, ID or address, but for simplicity we have just added one integer here. Next, in the main function, we want to read a particular record from the binary file. So we open the file persons.txt in binary mode. Because we previously wrote objects onto it using binary output, opening a binary mode ensures that data is read exactly as it was stored without any text conversions. So this line seekg jumps to the end of the file. Tellg function tells us the position of the pointer in the bytes, effectively giving us a final total size of the file. Then we divide that size by size of function that gives us the number of persons objects stored in the file. Next, we ask the user which record they want. Suppose the user entered 3. So then the program calculates the byte offset as that 3 minus 1 into size of object. That gives us the position of the third record. So seekg position statement moves the read pointer directly to that location in the file, skipping all the earlier records instantly. Finally, we read the object using that read function and display the relevant data. So the read function brings one full person object from that exact position into the memory, and the show function prints the result on the screen. So this approach lets us fetch any record directly, whether it is first, whether it is fifth, whether it is 100th, all in constant time regardless of the file size. So this is how databases and index-based systems achieve efficiency. So they rely on binary file access, random access using seekg and tellg functions. So far we have explored how classes and inheritance helps us model real world entities and how high file handling allows us to store and retrieve data efficiently. But now we will move into a new dimension of flexibility and reusability, that is the one that allows us to write generic programs that can work with any data type without rewriting the same logic again and again. This is where templates come in. Think of templates as blueprint for functions or classes that can adapt automatically to any type. For example, if you have a function to find the maximum of 2 integers and another to find maximum of 2 floats, you do not need to write two separate versions. With templates, you can write one generic function that works fine with any data type, that is integers, floats, characters, or even user-defined objects, all using the same logic. Let's imagine we want to write a simple function to find the maximum of 2 numbers. So we might write a function as maybe maxint for finding the maximum of 2 integers. That works great, but only for integers. If we now want to find the maximum of 2 floats, we will have to write a separate dedicated function to deal with float types. And again, if we want to compare 2 characters or double values or any other data type, we keep writing almost identical functions, the only difference being the data type. That is, the logic is same, but the data type differs only. So this is repetitive and very error prone. We are writing the same logic again and again just for the different types. So we tried to write a single template based max function. So template is a way of writing generic code, that is a code that will work with any data type. The idea is simple. We write function once and let the compiler generate type specific versions whenever needed. So the syntax for the function template looks like this. you write a template keyword, then angle bracket start, and you write type name and then T or any other label. Usually we write T. So T signifies a generic type that will be replaced in future by the concrete types like integer, float, double, and so on. So here the template keyword tells the compiler that this is a generic function. Inside the angle brackets we declare a placeholder type T. So T, as I just clarified, that it represents any data type. So when the function is called, the compiler automatically generates a version for the required type. Notice that we only wrote the function once, but it worked for integers, doubles, and even characters. So the compiler automatically created 3 versions internally, one for each data type used. So this is compile time polymorphism, also called generic programming. Now that we understand function templates, let's take it one step further and discuss the concept of class templates. Sometimes we want an entire class to be generic, not just a single function. For example, imagine we are building a simple box class that holds one value. We may want to write one box for integer, one for maybe strings, one for floats. So instead of writing separate classes like int box, float box, string box, we can write just one class template like this, like box with int stores integers, string dealing with strings, and box of double storing floating numbers. So templates make C++ powerful and reusable, and it lets us design algorithms and classes that are independent of the data types. In fact, many components of STL, your standard template library, like vectors, stacks, queues, are themselves implemented using class template. So templates reduce redundancy and it improves the performance because everything is resolved at the compile time. Now that we have explored how templates allows us to create a flexible, reusable code, let's look at a more practical example, a dynamic array class template. So here is the idea. Instead of fixing the data type of an array, we will design a class that can store any type of element, integers, floats, strings, or even user defined types. Let's take a look at this class called dyneArray. In this example, our dyneArray class can work with any type of data. The template parameter class element allows us to replace element with int, float, string, or even a custom class when we create a object. Inside a constructor, we allocate memory for an array of element objects. The set value and get value functions allows us to store and retrieve values at given indices. The get size keep track of how many elements have been inserted. The program then creates an object like this. Notice how we only wrote the class once, but we can now use it to create dynamic arrays for any data type, not just integers. So this is the real power of class templates: one design and infinite reusability. Now arrays are a great way to store data, but sometimes we want a more structured way to manage data, where we insert and remove elements following maybe a specific rules. That's where the stack data structure comes in. A stack works just like a pile of books. You can only add or remove from the top. So the principle followed behind the stack is called LIFO, last in, first out. This class of stack provides two basic operations: push to insert the element and pop to remove the element. Top variable keep track of the last inserted element. When we push, we increment the top and add the new element. Likewise, when we pop, we return the top element and then decrement the top. However, there is an important limitation. This stack only works with integers. If we try to push float values, there will be maybe truncated to integers, which means we are losing data and flexibility. So this brings us back to the idea of templates. Just like we made our dyneArray class generic, we can also make the stack class as class template, so it can handle any data type. Whether we want to create a stack of integers, floats, or even strings, one template class will serve them all. In our next segment, we will enhance this stack design by converting it to template based class, and later we will see how this concept is used inside the standard template library, that is STL, which gives us ready-made template based containers like vector, queue, stack. So to make our stack flexible and reusable, we introduce a template version that can handle any type of data. So in this version, we have declared our stack as a template class using class type that statement to make it type independent. Wherever type appears, it will be replaced with the data type we specify when creating an object, like of float, int, or even string. The member functions push and pop are defined inside the class itself. This means that both the template definition and its implementation are contained in one place. Now in main, we create a stack to work with float, and it just works. The same stack logic can now handle floating point values, integer, or even custom objects. Now in this version, we have separate out the declaration and their implementation, just like we usually do in regular classes. Notice how every external function definition starts with. So it starts with template class type and uses the syntax like stack, and then in angle bracket we write a type, scope resolution operator, and then function name. So this tells the compiler that these functions belong to the template class. They depend on the type parameter type. So what's the key takeaway here? By turning our stack into a template class, we have made it reusable for any data type. Whether we want a stack of integer, characters, or any other object, we can define member functions inside and outside the class. Both work perfectly fine in templates as long as the syntax is correctly followed. This flexibility forms the foundation of standard template library, where you find pre-built, highly efficient template based containers like stack, vector, list, map, and many others. Let's take a moment to understand what a self-reference class means. A self-reference class is a class that includes at least one pointer or a reference to another object of the same class. So this design allows us to dynamically create structures like linked lists, trees, graphs, where each element connects to another of its own kind. This is a basic singly linked list where each node points to the next one, forming a chain. A new node is created dynamically using a new keyword. The node's data and next are initialized. If the list is empty, both the head and tail point to this new node. Otherwise, a new node is added to the end of the list by adjusting or making some adjustments in the next pointer. Here we have two classes, element, which represent a single node, and a linked list, which manages a chain of these nodes. So each element object contains a data field and a pointer named next that points to the next element object in the list. So in the linked list class, we maintain two pointers, head and tail. Head points to the first element, tail points to the last element. When we call the add function, a new node is created dynamically using a new keyword. The node's data and next are initialized. If the list is empty, both the head and tail point to this new node. Otherwise, a new node is added to the end of the list by making some adjustments in the next pointer. However, there is a problem with this implementation. Again, it works only with integers. If we want to store string, floating points, or even complex objects, so just like our earlier stack example, we will have to rewrite the entire linked list class for each data type. So that is obviously inefficient. So the solution again, that is templates. So in this improved version, we use template to make both element and linked list classes type independent. Wherever we used int earlier, we now use a type parameter named type, and this allows us to create linked list for any data type simply by specifying the type when we create the object. The internal logic of adding and managing nodes remains the same, only the data type changes dynamically based on the template parameter. This demonstrates how templates and self-referencing can combine to build a flexible and powerful data structures. Now that we understand how templates help us design reusable and type independent data structures, we are ready to explore standard template library, the STL, which is a collection of pre-built template classes and functions that make working with data structures like linked list, tag, queues, vectors much faster and easier. So in modern C++ programming, one of the most powerful feature you will encounter is the standard template library known as STL, which is a collection of well-tested, reusable and template-based classes and functions that are designed to help the developers handle the algorithms, the storage aspects, the manipulation with very ease and efficiency. Instead of writing data structures like stacks, queues or linked lists from the scratch, we can use the ready-made, highly optimized versions in the STL. So STL is organized into three main components: containers, algorithms and iterators. So containers are the data structures that store collection of objects such as arrays, linked lists, tags, queues, vectors, maps or sets. Algorithms are built-in functions that perform operations like maybe searching, counting, sorting or transforming elements stored in your containers. Finally, the iterator acts as a bridge between container and algorithm, allowing traversal and manipulation of data without exposing the underlying structure. So together these components form a unified framework for managing data efficiently in C++. So the motivation behind STL is productivity and performance. It allows the programmers or developers to focus on solving problems rather than building a lower level data structures. So STL combines a generic, fast and tested library, and it also reduces development time while improving code readability. So STL provides a collection of ready-made type independent data structures built entirely using templates, and among these the vector container is one of the most widely used. It acts as a dynamic array, growing and shrinking as required without you worrying about the memory management. So you can think of a vector as a smarter version of an array. Unlike a fixed size array, a vector automatically resizes itself when new elements are added. It also provides a rich set of member functions for easy insertion, deletion and traversal. Let's start with a basic example. We create a vector of integers using that vector int v. Then we insert values using push_back function. When we print, the output will be 10, 20, 30. So these are the vector elements. So notice how easy it is. No fixed size arrays, no manual memory management or handling. So the vector class provides several handy member functions. Pushback adds a new value at the end of the vector. Popback removes the last element of the vector and reduces the vector size. Size function returns the current number of elements in the vector. Clear empties the vector, in other words it changes the size to 0. Front and back gives access to the first and last elements. Then int function returns the value at a specific position in the vector. These make vectors extremely convenient and safe to use. Notice that we have seen how vectors work with simple data types. Let's explore how powerful they become when we use them with objects. In this example, we will store and manage a list of employee objects with an STL vector. Here we define our employee class, which has two private data members, name and pay rate. To allow input and output directly through standard streams like cin and cout, we declare two friend functions. Again, you can recall that concept that we covered during operator overloading, the overloaded insertion and extraction operators. This enables us to input and display employee objects easily, just like we do with the primitive data types. The overloaded operator, one that intends to print a employee value, so it outputs the name and pay rate in the formatted way, and one is used to read the data from the user, prompting for both the name and the pay rate. This makes our class more intuitive and integrates seamlessly with the C++ IO system. In the main function, we declare a vector named myVector to hold employee objects. Each element of this vector will represent one employer record. We also declare a temporary employee variable entered val that we'll use to store input before adding it to a vector. Here the user is prompted to enter the details of one employee. After input, we use pushback to insert the object into the vector. The function size then tells us how many employees are currently in the list. Finally, we loop through the vector and print each employee using that overloaded operator. So this is a perfect example of object storage with automatic memory management, and the vector handles all the resizing and the memory allocation internally. So vectors allow random access to any element using either subscript operator or a cipher add function. So the add function checks whether the index is valid, preventing the accidental out of bound errors. So in this example, the user can enter a position and a program displays the corresponding employee record from the vector. The program successfully stores each employee as an object in the vector. You can add as many employees as you like, and the vector grows dynamically. So this shows the true power and flexibility of combining classes with STL containers. To summarize, vectors offer automatic resizing, fast random access, and easy insertion or deletion. They work beautifully with the STL components like algorithms and iterators, and since they are built using templates, they can store any data type. We have learned how vectors can store and manage collections dynamically, but the real magic begins when we combine the vectors with STL algorithms. So algorithms is a powerful built-in functions for transforming, searching, or maybe sorting with minimal effort. So we will now see how these algorithms work in hand with containers through iterators. Until now we have learned how to create and use vectors, even vectors of objects, to store and manage data. But what if we want to search and sort and manipulate this data efficiently? Do we need to write loops every time to process our container elements? Not necessarily. The standard template library provides a set of generic tools called iterators and algorithms that handle such operations with grace and efficiency. An iterator acts like a pointer that helps us to move through the container one element at a time. In this example, we create a vector named numbers and declared an iterator, it. The expression numbers.begin returns a iterator that points to the first element in the vector, while numbers.end function points to the one position past the last element. Inside the loop, we dereference the iterator using asterisk it to access the value it points to, just like dereferencing a pointer. This is how we can traverse the vector without needing to know its internal implementation. Iterators work not only with basic types but also with objects. Here we have a vector of employee objects. Each time we use it of name or it of pay rate, we are accessing the members of the object of the iterator is pointing to. We are accessing the members of the object the iterator is pointing to. So this makes iterators extremely versatile. They can navigate through any container and work seamlessly with user-defined types. Now let's make our iterator even more powerful by combining them with STL algorithms. STL provides a rich collection of some predefined algorithm functions that perform tasks like searching, counting, sorting, or modifying any container data. So these algorithms take iterator as an argument, which makes them work generically with any container, whether it is a list or a vector or a map. So in this example, we use find algorithm to search for a specific element. In this case, let's suppose a number 30. So the function takes two iterators, the beginning and end of the range, and the value to search for. If found, find function returns an iterator pointing to the found element. Otherwise, it returns the end iterator. Sort algorithm is another classic example. It takes two iterators, start and end of the range, and sorts the elements in ascending order. So the STL sorting algorithm is highly optimized, often faster than many custom written sorts. When working with objects, we can tell sort function exactly how to compare elements by passing a custom comparator function. Here compare by pay compares employees based on their pay rate. The sort function then automatically orders the employee list accordingly. So this illustrates how iterators, templates and algorithms come together, allowing STL functions to work seamlessly with user-defined data types. So that brings us to the end of our discussion on templates and STL and file handling. But programming doesn't stop here. As we move forward, we are going to take everything we have learned about logic, the structure, and the flow and apply it in a new and powerful and a more expressive language, that is Python. In the next session, we will see how to install and set up the Python, and then we will dive into the basics of the language, that is understanding variables, functions, and core concepts that make Python such a popular tool in the today's programming world. Thank you for your attention. I'll see you in the next session where we start our transition to Python.